And today we are talking about rational and irrational numbers in chapter 4. This is the last section, section 6. So you just told me what a rational number is. Rational is?
Fractional.
And so we can show it by using a fraction, showing our variables in a fraction. And Carson told us that if we have a fraction, a variable in the denominator, that variable may not equal
0.
If it did, that fraction would be
Undefined.
So rational numbers are predictable. There's either they terminate. We said 1/2 is that type of a fraction. 1/2 equals 0.5. It ends. It has an ending, so we know it is rational. The other option is it repeats forever. And somebody give me a fraction that repeats the same forever. 1/3 is the classic example. So what number is repeating? 0.3 repeating forever. So what will be the 151st digit? 3. And what would be the 2,000,000th digit? 3. It just says 3 is infinitely. When we use those numbers, we have to round them. The best thing is to leave them as a fraction. And hopefully, somehow, you don't have to deal with the fact that they repeat forever if you've left them as a fraction. Then we have the whole set of irrational numbers. Sometimes it's best to think of a definition of an opposite thing. Rational and irrational are opposite, right? By looking at the definition for the first thing. So if a rational number terminates, then an irrational number doesn't terminate, which means it never ends. It goes on forever. Some kind of a decimal number that goes on forever. And if a rational number repeats, then we would say an irrational number never repeats. If a rational number is predictable, then an irrational number is
Unpredictable.
right. So, oops, I just gave it away. We've talked about the biggest group of irrational numbers. And that big group is what, Rishi? Of what? Like, is the square root of 100 irrational?
No.
What is the square root of 100?
10.
10, and that is a rational number that terminates. So, Rishi, what is the square root of 9? That's a prime number, and it's rational. So we have to say something different. Moya?
The square root of any number that's not a perfect square.
That's it. The square root of any number that is not a perfect square. So we would start with, what's the smallest integer, or what's the smallest whole number that if we stuck it inside the radical would be irrational? 2. Square root of 2. Now square root of 0 we can find. Square root of 0 is
0.
Square root of 1 is 1. Those are perfect squares. But the square root of 2, it's 1.4 or something, and it goes on forever, and there's no pattern. What's the next one up from square root of 2? Square root of 3, right? Now, is the square root of 4 irrational?
No.
No, the square root of 4 is rational because it's 2, right? So, irrational, again, neither terminate nor repeat. Square root of 3 is another good example. It's possible there are others. Okay, so we have this entire set. We've talked about this set of numbers before, real numbers, and we're going to revisit it again. So we have a giant set of numbers that mostly are the numbers we work with, called the set of real numbers. And the two big categories of real numbers are what we're discussing today. So who can tell me what those two big sets are? Caroline.
Rational.
Right. So we have rational numbers here and irrational numbers over here. There aren't as many subsets. There aren't a lot of subsets for irrational numbers. We know pi is an irrational number. And like Moya said, it's a circumference divided by the diameter of a circle. That's how that was found. We'll talk about that more when we get to areas pretty soon. But the other example would be the square root of some non-perfect number. So it's a huge, huge number of, bless you, it's an infinite number of numbers we could find that are not perfect squares. And here's just one little example. Okay? All of these types of numbers have no end and do not repeat. But when it comes to real numbers, we have some subsets. So first, the rational are fractional. So looking at our number line in front of the classroom, these are numbers, every number you see there is rational, and all the in between, right? Any little fractional pieces in between, like 1/3 or -1/2, okay? But if we were just to not include those in between numbers and only included the blue numbers, the black 0, and the red numbers, what do we call that set of numbers?
Integers.
Very good. So now we have taken away the fractional pieces. So the set of numbers became a bit smaller. And now, if we take away the red numbers from our number line, all those negatives, and we only include 0 and the blue numbers, 1, 2, 3, 4, 5. What do we have?
Natural numbers.
0 and 1, 2, 3?
Counting.
Natural
I don't hear it.
Natural.
I hear positives, but what about 0? 0 is not positive. And Caroline, say it. Whole numbers, that's right. Okay. You all are giving me the name of the smallest set, although it is infinite in size. Isn't that weird? That these smaller sets are still infinite in the number of numbers in them? It's kind of a mind-boggling thing. But what do we get when we take away the 0 from the set of whole numbers, everyone? That's it, counting. And the other name is natural, so let's add that in, because that shows up in different math situations. Some math tests will not say counting numbers, it'll say natural numbers. Some math textbooks don't say counting, they say natural. And that's an easy, I feel like it's a comfortable word to use, because we know counting numbers are just the first things probably people did. Like, I have 1 apple, 2 apple, 3 apple. You know, before they even used 0, people probably started counting 1 and 2, 3. And that feels natural, doesn't it? So that word is a nice word to pair up with counting. Okay? So there's your big sets. So now the question is, can you identify whether an expression is a rational or irrational number? Okay, so jot these expressions down, and then underneath them, are they rational or irrational? Okay, 3/4. I bet you know. I'm going to count you down. Tell me, is it rational or irrational? 3, 2, 1. Rational. Very good. It terminates, doesn't it? What is 3/4 as a decimal number?
0.75.
0.75. So we will say definitely rational. We know everything about it. And the square root of 5. 3, 2, 1.
Irrational.
You know, we just went all through that definition of how a non-perfect square number in a radical is a number that goes on forever and also has no pattern. Okay, let me count you down here. Let's see how fast you can determine this one. This is 1/3. 3, 2, and 1. Okay, raise your hand if you say irrational. Raise your hand if you say rational. Good, you're right. It's rational because it repeats the same number forever, so we know everything about it. 0.3 forever, right? Just like this was a terminating, we know everything about it. That one's a repeating, we know everything about it.
Oh.
Okay, and the final question. This is a tricky question, so take a moment to think about it. Okay, now that you've thought about this a little while, the answer is this rational or irrational? 3, 2, and 1. I think I hear more rational. Raise your hand for rational. Raise your hand for irrational. Ooh, it's half and half. Raise your hand for rational. Rational? Raise your hand for irrational. It's still half and half. Okay, who feels so strongly about your answer that you can convince us all? Rhett, what do you think it is?
Rational because the square root of 25 is 5, the square root of 81 is 9, so 5 minutes is 5 minutes.
And 5 9, is that not rational?
Oh.
Is this rational?
Yes.
Yes, this is rational. Very good. So just because you see a square root, does it mean for sure that that expression is irrational? No. These are perfect square numbers, right?
I don't get it.
We learned you can take the fraction and separate the two. Numerator, Sarah, we learned that you can separate the numerator and denominator. And what is the square root of 25? And the square root of 81? So let's end up with this fraction, which we can find. And 5/9 we found is 0.5 repeating. Now, if you do that division in a calculator, it will eventually round it to the last digit available on your screen. And it will round it up because the next digit would be 5, right? So it would round it up to 6. Okay, our final topic is comparing things today. Comparing real numbers. In this case, we're comparing a rational with an irrational. So does anybody have a hint? Oh, first of all, what do we mean, what are we doing when we're comparing numbers? What could we possibly say about these two numbers? Sarah?
Well, when you say compare, you mean like the equal sign and
Yes, okay, so you're saying it. Greater than, less than, or equal. Looking at the first sign here, when you read it left to right, going from the left to right, we're crossing the big section first. So what is this sign? Greater than, right? The second sign, we're reading it left to right, less than. Okay, so what strategy could you use? Here, Adrian.
Well, the closest square number is 8 and 9, so this can like that.
Okay, did you hear what he said? He is doing this. He is approximating the value of square root of 8. He says the closest perfect square to 8 is 9. Square root of 9. And the square root of 9 is what? 3. So he thinks that this square root of 8 would be a little less than 3. Don't you think that's a nice strategy? Right? So what's greater, 4 or the square root of 8? 4, right? Because it's definitely greater than 3. And that number, square root of 8, is a little less than 3. So that's what you're doing. Now, if you had a calculator and the opportunity, you could calculate the exact square root of 8, and you would find something like what he said, like 2.8 something. Okay? This is a little trickier. Actually, it's a lot trickier. It's fractions. That's fine. Okay, so you're trying 4/5 or the square root of 4/5. I mean, the first thing a person might think is that the square root of 4/5 would be what? What do you think a person would be, who thinks it might be less than right away? Okay, that about half the people are raising their hand. Who thinks it might be greater than right away? Only a few people. So a lot of people are not saying either. Okay, fractions are really kind of tricky. I mean, somebody give me a, well, let's just take a fraction that we're really familiar with, like 1/2. What happens if I square 1/2? 1/2 squared is really equal to 1/2 times what?
1/2.
1/2. And that equals what? 1/2. Isn't that weird? When you take a fraction and square it, do you get a bigger fraction or a smaller? Isn't that weird? So, if I take 1/4, let's take the number that we ended up with there after squaring, and we take the square root of this number, isn't that just the square root of 1 over the square root of 2?
Yeah.
I'm sorry, over the square root of 4?
Yeah.
And what is the square root of what?
1.
And the square root of 4? 2. So look at that. The square root of small little 1/4 is 1/2 greater. Isn't that weird? It kind of makes your brain hurt a little bit. Fractions work kind of in a reverse way than integers do. If I take 3 and square it, do I get a bigger number or a smaller? 3 squared is 3 squared is 9. I get a larger number than the 3, right? The 3 itself is smaller than 9. When I square it, it makes sense. I get a larger number. But when I take 1/2 and square it, I get a fraction that's actually less than 1/2. Isn't that interesting? It has a reverse effect. Okay, so how are you going to approach this problem? Here, Josh.
You are going to find the square root of 4 and then the square root of 5.
Okay, what's the square root of 4? He's doing this. He's estimating. Okay, so square root of 4, he says, is 2, and the square root of 5 is?
It's probably 2.2 or 3.
Okay, 2.2. Now that's interesting, that's kind of hard to work with, right? What could we do to get the decimal out of the fraction?
You could move it over by multiplying it by
Multiply by
10,
10,
but then
multiply by 10,
as well.
so 20 over 22. What do you think's greater, 4/5 or 20 over 22? Which one's closer to 1? 4/5?
Yeah.
Who says 4/5 is closer to 1? Who says 20 over 22? You're right, it is, isn't it? So really, the square root of 4/5 is greater than 4/5, just like we saw with the previous little examples. You know, another way to look at this is changing them to decimals. What is 4/5 as a decimal?
0.8.
Okay, I hope you're all following. And so we would be taking the square root of 0.8, right? And no, we're going to have to make it a 2-digit number, right? Remember when we took the square root of 0.36? What did we get? Wait, you know what? This is a little frustrating listening to all. What is the closest perfect square to 0.80, Caroline?
9.
Well, okay, because you're saying it's close to 0.81, right? It's approximately that, so this equals approximately 0.9, right? What's greater, 0.8 or 0.9? 0.9. So again, we have the right symbol here. The square root of a proper fraction is a little greater than, or maybe a lot greater than, the fraction that was in the radical. Okay, so be very careful when you're dealing with that in your assignments today. Here's the very one we just did, if you can remember. What is greater, 1/4 or the square root of 1/4? And the answer is
Square root of 1/4.
which we already said is 1/2. 1/2 is greater than 1/4. Okay, try this. Square root of 7 or 3. Educated guess.
Well, I was just 0.2.
You now have 20 minutes in class to begin this.
We finished.